Let me start by saying job well done in the lab today. You were given a DIN rail, some terminal blocks, some jumpers for those terminal blocks, and 2 relays. And you were asked to build this circuit where we have a push button which would activate K1, and then this here on rungs 2 and 3, which you'll recognize as a seal-in circuit, otherwise known as a latch. And the way it works is when you push this run button, this entire rung will evaluate as true, right? The current will flow from the 24-volt supply through the run switch, through the closed contacts of K1, and it will activate relay K2. Once relay K2 is activated, it will seal in via this contact right here. And now, even when you release the push button, it will continue to run. Right? It is sealed in, it is latched. It will continue to run until you either remove 24 volts DC or until K1 is activated, which will open these contacts. So we have a run button to activate this rung, a seal in circuit, and then this is the stop button up here using K1. For those of you who've seen this circuit before, yes, it's a little bit overly complicated, but that was done on purpose. One of the reasons was to explore what it meant to have these terminal boards and how to connect the various wires. For example, we started on terminal board 1, pin 1. We connected that to a push button, which is off the screen. And then we went to coil A2 on K1. And from there, we ran back to ground on terminal board 1, pin 5. So here it is. Terminal board 1, pin 3 on the push button, pin 4, which you would have written right here. A wire was then run to the coil of K1, which is on A2, and you would have written A1 on the diagonal right here. And finally, we're back at terminal board 1, pin 5. This was a good exercise because you got to work with the relay. And it was this one right here where we have a coil, and then we have double pole, double throw contacts. For example, if we use the IEC numbers, which are in the parentheses here, we have a coil on A2 and A1. We have this common contact on pin 41. We have a normally closed on pin 42 and a normally open on pin 44. And on the other side of the relay, you have the same thing. Pin 11 is the common contact, pin 12 normally closed, and pin 14 normally open. That was important when you went back to this ladder diagram because you had to write the relay's pin numbers right here. So you wrote this on the diagonal, and then you wrote another designation on the diagonal here. Before we start today, let's do a class map so we can see where we are and, more importantly, where we're going. Up until this point, we've been largely focused on the physical. And if we mind map this, we've talked about terminal blocks, highway diagrams. We've also talked about the relay. The relay has an armature, a coil, and things like normally open and normally closed contacts. We also looked at the pinout from the data sheet. Closely related to relays were contactors and motor starters. Okay. While we're talking about the physical, we've also explored the PLC. We've mentioned the I/O, which is the input-output of the PLC. We talked about indicator lamps, input block, output block, and from there was type B for source, type Victor for sync, and of course the type W for the relay. On the PLC, we talked about status lamps, model number, or we could better say Micro800 family. But there's one thing we haven't really talked about yet, and that is Code. We have not talked about programmable logic code. The closest we've come so far is the second part of today's lab, where I asked you to open plcfiddle.com and work out this code school tutorials. By the by, do you recognize this circuit right here? So we have a start button, a stop button, we have a relay called motor, and we have a contact over here. Check this out. When you hit the start button, oops, there we go. When you hit the start button, you'll notice that this goes green. So right now we have activated the motor. This coil, which was normally open, has been closed. And when we release the start button, you'll notice that this particular circuit has latched on. That is the exact same thing you did in the lab here. Same circuit. Here's the start button. Here's the stop button. Now granted, we have it as a slightly overly complicated relay coming from rung 1, but it's still the stop button. And here is the holding circuit to seal in that latch. So anyway, that's the closest we've gotten to code so far. Today we're going to explore structure. Structure is going to be extraordinarily important to us. But in order to understand that statement, I need to show you why. Let's talk about our long-term goals. I would argue that the target we want to hit towards the end of this class is to program sequential machines. In order to do that, we're going to have to learn ladder logic. We're going to have to learn the memory structures. Timers and counters will be important. And then, and this is the key one, we need to learn about user-defined function blocks. When we get to that point, we can talk about sequential machines. For instance, several times we have talked about the motor starter. So here's our in block, here's our out block from the PLC. And without adding all the wires, we talked about the motor starter that's activated by the PLC. We drew some lines to talk about the mechanical relationship between the motor starter coil and the contacts. So right here we'll just say to our three-phase motor. And those would be the heavy contacts that we mentioned. We also spoke about an auxiliary contact that would allow the PLC to monitor the fact that that motor starter relay is indeed activated. So that's our example. Again, motor starter, we have feedback. Our target, I said, is the user-defined function block. We want to build a block of code that will allow us to control and monitor that motor starter. So let's call this function block motor starter control. We'll give it some inputs, X enable, X sensor. X is actually Boolean, so we'll call it Boolean reset. And time to close. Yes, that is the way I wanted to spell that. On this side, let's give this block some outputs. We'll call it X valid. We'll call this one Boolean coil drive. X busy. A Boolean for fault. And a error code. This is the target that we want to hit. towards the end of this class. It's a block of code that's completely encapsulated that will allow us to to control and monitor this motor starter. Let's see if we can make some sense of it. So enable, so we're going to put a rung here. Enable will be a contact that says turn this thing on. So turn on the motor. That's not so bad, and that makes sense. It goes to the enable. We should probably spell enable correctly. That'd be a good idea, right? So E-N-A-B-L-E, better. So that's how you turn the motor on. You have this block of code and you enable it. We have the coil drive right here. Whoops, we want a coil out there. Okay, so this goes to motor starter. We have the sensor, which will come here, and that is the auxiliary contact. So we should color code this. So we'll let the auxiliary contact be purple, right? That's the auxiliary contact, and that's this one right here. So the steps are, this is commanded to turn on. It will activate the coil drive, and then it will monitor to see that the coil actually closes. If the coil closes, it will activate this rung right here, which says it's valid. Everything is good. If something goes wrong, it will disable the drive. It will no longer be valid, but it will issue a fault. And will also give you a number. So some number in here will tell you what the fault code is. This type of programming is our target. This is where we want to be at the end of the class. And the reason I bring it up today is because I wanted to show you something. See these X's? I mentioned those before. Those X's signify a data type, in this case a Boolean. So the enable is either enable or not enable. The sensor is either active or not active. Other things, like time here, for instance, would be a box. So time might be 100 milliseconds. And this would be useful because that motor starter doesn't activate instantaneously. As soon as you issue the electrical command, it takes a certain amount of time for those contacts to come close. So what this does is the time tells this block, you know what, just ignore the fault for a minute, right? Because it's going to take some time for this auxiliary contact to respond. If it responds within 100 milliseconds, then don't send a fault. On the outputs, we have Booleans, and then we have this number here, or this data type here, for a double integer. If that was an uncomfortable jump, we could look at this a different way. We could say that PLCs are like onions. What we're really talking about is the structure of code. Talking about the structure, and we're talking about a hierarchical design. Right, where we have layers upon layers. We build our code block upon block, and it makes things so much easier. Knowing that this is our target, I would argue that it's important that we develop the muscle memory and the discipline to use these data types as we go along. That way, we won't have to unlearn what we learned. We'll be ready to use these as we need them. If you're curious, this does have a name. It's called Hungarian notation. Are you ready to talk about code? And the answer is, well, not yet. We're almost there. What we need is we need a few models, or we need to take the model we have of the PLC, and we need to add some complexity to it so that they're ready to graft our code onto it. This is our model so far. We have field devices, and these are the switches and sensors. We have the programmable logic controller. Then we have the field devices, which are the solenoids, the panel lamps, the motor operated valves, motor starters, and all of the machinery that you're going to control. There may be a feedback path. For instance, you might have a tank. That tank will have a fluid level. An ultrasonic tank level indicator could be used to determine that level. This process might have an exit for this fluid, and then there's likely to be a pump to fill the tank. The level indicator is an input, and the pump is a field device which is to be controlled. So as the water level rises, you might turn the pump off. Simple enough. And that is an example of this feedback loop that we talked about. The feedback is a physical thing that's changing. Again, in this case, the water level is coming up and it's being measured and it's being controlled. All right, with that said, I'm going to jump over to the other side of the screen, and then we're going to go look at what happens inside the PLC itself. Now, this is a model. This is one way to look at the PLC. Now, there's a clock here, and you could think of that as the clock will move in a clockwise direction, and the PLC will do this about 1,000 times a second. At 12 o'clock, we see that the PLC is doing some system maintenance stuff. That is when the microcontroller here is talking with the memory, it's talking to the FPGA, is doing everything necessary for the PLC to support itself. At 3 o'clock, we have what's known as an input scan, and it looks like this. The PLC spends most of its time completely blind. It doesn't look at the inputs, it doesn't care about the inputs, it doesn't know what the inputs are doing. But every once in a while, it goes peekaboo, just like that. When it's at 3 o'clock, it opens its eyes, and it says, oh, I have an input bus. I have some physical input, and I'm going to look at what those are. I'm going to go down the list of all the inputs I have, and I'm going to take those and put them into memory. So again, most of the time it's completely blind. Once every program scan, it opens its eyes, grabs the information, and closes again. Just peekaboo. Now, the system maintenance and the input scan are completely outside of your control. That's something that's established by the firmware. This is in your control. These are your programs. We're going to talk about code structure, and in this class, especially at the beginning, we're going to use a trio of programs. We have a program known as input map, we have a program for control, we have a program called output map. And you'll notice that the first thing that happens, again, as the clock spins around in a clockwise direction, is that we execute the input map, then we execute control, then we execute the program map. When that's done, we're at 9 o'clock here, and that is an output scan. So that's the opposite of this. So for all this time, the PLC has said, those are my outputs, those are my outputs, I don't care, those are my outputs, I'm not changing them, those are my outputs. And when it hits 9 o'clock, it goes, there's my outputs. And it sends it out to the world. Then it slams its eyes shut again and says, those are my outputs, I don't care what they are, those are my outputs. It's kind of an interesting process. Again, that's outside of your control. So 12 o'clock, take care of yourself. At 3 o'clock, go get your inputs, put them into memory. At 6 o'clock, perform the various functions that your user has programmed for you. Again, we use a program trio, input map, program control, and program output map. 9 o'clock, take whatever the user programmed, send it to the output, and then do this loop. Again, about 1,000 times a second this occurs. What I'd like to show you here is the same thing, except drawn slightly differently. So you'll notice the looping nature of it here. Again, this is something the PLC does 1,000 times a second. It'll run through these and loop back, and it'll run through it again 1,000 times a second. This should look more familiar. You have your input block where your field devices connect. Here's your output block where your actuators and indicators connect up as well. You'll notice that there is a screw terminal to memory operation that's performed here. Yes, I am conflating two ideas. I'm conflating the fact that the input scan and the input map, I'm assuming those are the same thing as far as our purposes are concerned. I hope you'll forgive me. I'm also conflating the output scan and the output map. What I'm showing here is an analogy. It's not quite true, but for our purposes, it's close enough. And personally, I think it's a good way to look at it. Anyway, as we go around that loop, you can see this part here where it takes the screw terminals and converts it to memory. That is the peekaboo that I just told you about. This happens once a program scan. Again, the screw terminals are read and they are stored in memory. Your program, your control program, is a memory-to-memory operation. You may think you're writing to, to turn the pump on, for instance, but you're not. What you're doing in this program is you're writing to a memory location. Later, that memory location is sent to the screw terminals for all the output blocks. Again, one big giant loop. This is yet another way to look at the PLC. Here are the sensors, all our inputs that we talked about before. This is the input module. That is physical hardware. Right? It's real stuff right there. That's what the input module is. Then we have memory. We have the microcontroller and FPGA and memory up here. We have the output image, which is more memory. And then we have the output module, which is, again, a physical device. Finally, that goes to the actuators. Remember that clock model I showed you? At 3 o'clock, we had the input scan. So what happens is at 3 o'clock, we take the data, the values that are on the input module, and we transfer them into the input memory. So that's a screw terminal input to input image memory. When your program scan reaches the 6 o'clock position is when your programs get executed. And those are stored down here in program memory. What they do is they operate on memory to memory. So they may move memory from this input image, they may move it up to tag memory, or they may make calculations to compute the output image. When we hit 9 o'clock on that program scan, the output image is transferred to the output module, and that's again hardware to control the actuators. A few other things here. This is your PC. You program, right, with this link right here, you program the PLC, and there's also firmware that does need to be updated occasionally. I believe we're on version 12 as I write this note. Let's see, what else? We have this communications block up here. The communications allows the PLC to talk to the human-machine interface or the variable frequency drive, a network, or maybe another PLC. Just remember, these are all models that suggest how the PLC work. We have this one with quite a bit of detail. We have this model with a little less detail. And then we have this one with even less. Again, program scan, 1,000 times a second. Oh goodness, that took forever. Are we ever going to get to some code? We are almost ready to fire up Connected Components. Before we do, let's talk about our first program. You'll recognize these as the input block and the output block of the PLC. And we do this because it's really hard to talk about ladder logic without seeing how it's connected to the outside world. So we'll let this be input 0, 0, and we will connect a push button to it. That push button will be labeled push button left. Let this be input 0, 1. We'll put another push button here. This time we'll call it push button right. On the output, we'll have output 0, 0, and we'll connect that to a blue panel lamp. And finally, we'll have output 0, 1, and we'll connect that to a green, oh, let's do that better. And we'll connect that to a green panel lamp. And here's the control rule. If both left and right, comma, then blue. So if both the left push button and the right push button are activated, activate the blue panel lamp. If either left or right, then activate green. Okay, so if either left or right is pushed, then you'll activate green. If both are pushed, you'll activate blue. There it is, Connected Components Workbench, Standard Edition. File, New. We'll just put this on the desktop as example 1. Controllers. We will use the simulation, which exists as a LC50. Here's the firmware version, version 12. Select, add to project. We'll start with our program trio. We're going to add a ladder diagram. We're going to add another ladder diagram. And we'll add a third ladder diagram. We will rename these. We'll call this program in map. We'll call this one program control. And we'll call this program out map. So here's our program trio: program in map, program control, program out map. You'll notice each one has local variables associated with it. So for example, the one that's highlighted here is only associated with program out map. There are also global variables that allow the programs to communicate with each other. And that's something we need to take care of right now. So we'll go into global variables, call this global Boolean push button left. That global designation allows us to share it amongst programs. Global Boolean push button right. Global Boolean panel lamp blue. Global Boolean panel lamp green. And because these are globals, they can be shared amongst all the programs. Let's start by constructing our input map. You remember the input map took a screw terminal input and related it to a memory location. So for our purposes, we take this, which is an examine if closed contact, and we want a input output, and we said we wanted input output embedded digital input 0, 0. And we said that was our push button left. Now we go to the global variables and push button left. We insert a rung below. We find our input. So embedded digital input 0, 1. We relate that to a memory location. This time global, and we'll call it right. Okay, that's it. Moving on to the output map. You remember the output map takes a memory location and relates it to a screw terminal. So we're going to take that blue panel lamp, again a global blue, and we're going to relate that to the output that is embedded digital out 0, 0. And one more rung here. And we'll take the global green, so global Boolean panel lamp green, and we'll put that to digital output 0, 1. That completes our input map and our output map. Now we need to work on the control. And our rule was if both left and right, then blue. So we'll need if global left and global right. Right? So if both of these conditions are true, there will be continuity across this rung. And we want to associate that with the blue panel lamp. Right? So if both the left and the right are pushed, this will activate. We'll insert a rung below, and we'll need a branch. So this one is if left and right activate green. Okay. Well, that's it. So we have our program trio. Let's see if we got it correct. So we're going to start the simulator. We're going to turn the simulator on. And then we are going to download, actually we'll hit this disconnect button, which should automatically launch the code. The simulator lives on this computer and you access it via this IP address. At this point you want to tell it to run, so change to run. And now when we look at our simulator, we should see the power lamp, we should see the run. In the real world, you would have switches connected, but the simulator allows you to just push buttons, right? So this is digital input 0, digital input 1. So if we push this, yep, sure enough, this would be our green panel lamp on digital output 1. If we select this, it's still lit. And if we select both, we should get the blue panel lamp, which is connected to digital output 0, 0. So we have been successful. Something I like to show you here, if we go to our input map, you'll like this. We go to our input map, and if we push this, you see that this evaluates true, and the entire rung lights up as red. Likewise with this, the entire rung. We see the same thing for our program control. If we were to push this button, that would be the left. You can see that this is activated. In fact, this rung is entirely true because either left or right will activate it. If we push the other button, now you can see that rung number 1 is true. And finally, our output map. And if we push 1, this is our green panel lamp. And if we push them both, this is our blue panel lamp. It looks like we were successful. We had a push button left, a push button right. We had panel lamp blue, panel lamp green. If both left and right, then the blue lamp would light up. If either left or right, then the green panel lamp would activate. We mentioned namespace. Globals were part of that. We had our program trio. Each of those had their own local memory. These programs would talk to each other indirectly by writing to global variables. For example, program in map would write to global Boolean push button left. That was then picked up by program control. Program control would write back to a global. One of the things it wrote was global Boolean panel lamp blue. Oops. And that was then used by the program outmap to send the information. Remember, that was G for global, X for Boolean, and then this was the name associated with that tag. We did see some I/O. So one of the names we saw looked like this. And this is input-output, embedded, digital input, and this is the number associated with it. So this is input number 1. Not the first input, mind you, but input number 1. The first input is input 0, 0, and the one we looked at here is input 0, 1. While we're here, I want to mention another type of system variable because I think it's useful to our conversation and perhaps a good way to end for the day. So, system variable, first scan. Remember, we talked about a system scan and we equated it to a clock, right? So we're always rotating in this direction. So we had the housekeeping up here at noon. We had the input scan. We had your program trio. And then we had the output scan. I mentioned this variable called system scan because I think it has an interesting property that you should be aware of. And that is when the PLC is put into run mode, right? The very first time it's put into run mode, this thing starts to execute, right? We start spinning around this circle, 1,000 times per second, give or take. So 1,000 scans per second. On the very first scan, the very first time this thing goes around, and for one scan only, this variable here will be high. Suppose you had a memory location and you wanted to make sure that it started with the number 50. What you would do is on the first scan, you would look for this variable to be true, and if this system variable was true, you would move the number 50 to that memory location. That would occur once and only once when the PLC started. Let's do a quick review and then we will call it a day. Our long-term goal is to get to sequential machines this semester, and we said that the user-defined function block will be the primary tool that we use to get there. This is a feature of the IEC 61131-3 code that the Micro800 family is programmed upon. To impress this upon you, we talked about the motor starter and this somewhat confusing at this time block of code, which we will use to control that motor starter. And we incorporated a lot of features into this, things like that it takes time for that contact to close, the fact that we can have faults, and we even can tell the operator what the fault was, by giving it a certain number. The main takeaway was that there were different data types. We didn't describe them in detail, that's another day, but there are different data types, and we will use Hungarian notation with camel case to identify our types. We did mention code layers and the fact that our PLC code will be built as a hierarchical structure, and that sounds confusing at this point, but it will make our life significantly easier as we go along. From there, we showed various models of the programmable logic controller. We started out with this one where the PLC was sandwiched between two devices. We talked about feedback being a physical thing. For example, the level of water in a tank is an example of the feedback that is measured for this system. And then we use the pump in this example to control the water level. We went into connected components and we built our first program. Internally, we talked about this structure, which we defined as an AND structure. And we also defined this structure, which we called an OR. So in the first rung, if this and that evaluate as true, then this coil will close. And here it's either, because you have two paths. You could go through this top path or you could go through the bottom path. So two paths give you an OR. We'll explore this in much greater depth in our next lecture. We mentioned the namespace inside the PLC and the fact that these individual programs, right, our program trio here must communicate with global variables. This was an example of a global variable, G as a prefix for global, X for Boolean, and then we gave it a name. And the final thing we talked about were system variables, where we described this as an input-output. Embedded, by the way, embedded refers to the fact that it's actually built into the PLC as opposed to one of the plug-in modules or one of the expansion modules. So our base PLC has embedded I/O. These last two digits identify the specific input. In this case, it's input 0, 1. That's it for now. Come back after Labor Day and we will take a deep dive into ladder logic.